So yesterday I told you about the simple idea that if I have a joint system, a system that has two particles, at least two particles or more. So if each of them has some individual property, which I wrote like what, Q and T, I think. So one has a Q property, another of them has a T property, some T property. Then I should be able to write a joint eigenstate of these two particles that consist of these two systems, where I measure each individual property of one particle in this two particle state, and that returns me this thing. Right? And in order to do that, I told that the systematic way to do that will be, this will be represented by a joint kate like this, and the object that will act on this has to be also of this dimension. And the way to represent that is by this. So this is the property 1 and this is the property 2. Okay. The way to represent that will be this. Then this will act on QQ, identity T, and give you Q, Q, T. Right? So this is the general way, this is the idea that why you need such a thing. And then we expanded on that idea. Then we learned how do I operationally work with such a thing, such a higher dimensional direct product space. Then I can have even properties like this, which is a joint property of this QT basis. And then they will act accordingly, right? The Q will act on Q, the T will act on T accordingly. Okay, so then I ended by saying, giving some example of that how do I operationally construct, how do I construct those operators actually? And I showed you two different ways to do that. So I talked about this operator, which was beta 2. So I'm just revising, so I'll not write everything. So on this basis, on a two-dimensional basis, which has two states, plus and minus, and the joint states will be plus plus, plus minus, minus plus, minus minus. So I should be able to, if I have to express this operator O12, it should be in this joint basis, right? Plus plus, plus minus, minus plus, minus minus, plus plus minus, minus plus minus. So this is just a shorthand of writing this. If I actually should be writing this, but I just shorthanded this like this. So then each entries I have to compute this. So let's say first entry will be O12 plus plus, and O12 plus plus is plus plus beta I plus plus, that beta acting on this. You can show they will split like this, and so on. You can compute all these elements like that. So if your beta is, I showed you beta is A, B, C, D. If beta is this, and then there is another beta 2, I is just identity. So then I showed that this will be just A00A, B00B, C00C, D00D, which you can also would have done directly if you would have just multiplied this with identity. If you have directly taken a direct product, but you can also construct it element by element. Okay, these are the two ways to do that. So everybody understood those things, right? Okay, so then I continued on this exercise. I told you how to do that for spins, and for spins, I told you, for example, if I do, for example, the reason I was looking for this, because I wanted to explain you this kind of Hamiltonian, that let's say I have the general idea is to describe this kind of Hamiltonian is that, let's say these are simplest Hamiltonian that describes a magnet. So a magnet is basically a bunch of spins, right? Some spins, right? And each of them are quantum mechanical, right? So they are spin half object located at, it is not necessarily just magnet, anything that has this kind of two-level structure that can be described like that. They could be pseudo spin actually, not spin. Many times there are objects which behaves like spin, but they are not themselves spin. For example, if you think of the Valley quantum number, I don't know if anybody have heard this Valley quantum number of graphene, or there are many other objects which can effectively act like a spin. So then for any such thing which admits such a description, you can think it as if it's like a spin system. And the way to describe them is, so ideally you want a Hamiltonian for this spin system. This is actually itself a very interesting problem, that what are the possible spin Hamiltonian I can write. So what is a Hamiltonian? And Hamiltonian is a scalar. So how many ways you can combine these spins to form a scalar? Right? So one such way is S1 dot S2. So this is the simplest spin. So this is 1, 2, 3, 4, 5. So S1 I dot J, right? Where I and J are nearest neighbor. This I and J are nearest neighbor. And there are even simpler models you can think of. You can think of a molecule of two atoms which has effective spin half, then you can write an effective spin Hamiltonian for that kind of system. And there are very interesting physics of this, that how come, why do I write such a spin Hamiltonian? Because if I think of a magnet, the objects that we have are atom, electrons, and ions. Why not the atoms, the electrons, charge, the ions, all these other property, all things are washed out, and I'm effectively working with this Hamiltonian. So this is a very interesting problem of its own, which you will learn maybe in advanced condensed matter and all. So for example, you can ask this question: if I have an atom, if I have a solid, there are atoms in it. A solid is a very complex system, right? All kind of things are going on there. Bunch of atoms interacting with each other and all that, which you are probably learning in solid state physics. Then it turns out that there is a regime where it can happen that the electrons, because of Coulomb energy, it's very costly for an electron to hop from one side to another. Because if they hop, their Coulomb energy barrier is very high. This is an effective scenario. Okay. When that happens, then you can show that each electron has a charge and spin. So let us write it like E and the spin, E and the spin, E and the spin, right? This is an effective picture for this. Right? Then the electron, the charge part cannot move. The charge part is frozen. Charge sector is dead, but the spin can still fluctuate, right? So then you can write down, do a second order perturbation theory, which you will learn in advanced condensed matter. Then, although your original Hamiltonian is of this form, that T tells you the exchange hopping amplitude, which is basically if the atom has a wave function like this, it tells you how much is this overlap. So you can write the Hamiltonian as, so this I to I plus 1, this tells you this to this, like two locations, plus U, which is I. So this is a little tricky, because here you have to write I, but this is not just this actually. So yeah, so this is this. It's inner product with I and I. So this is actually the form of writing it. It's a little complicated. So then you can do a second order perturbation theory, which gives you this T square 4T square by U is I dot Sg. So this is the origin of magnetism. They are insulator because the charge cannot move, but they are magnets, magnetic insulator, and you can already see a separation, like charge spin separation, and there are much more exotic thing happens there, because the spin can also act like as if it is made of some other subparticles, and there are many interesting physics of that. So I'm just telling you the origin of thinking of such a model, that why do I care about such a model. These green dusters are not here. Okay. Anyways, so yeah, this is the problem with this duster. It itself caused the. So this is one of the origin of such a model. There are many other origins, but there are many other ways to think about it in different contexts. So I want to simply describe, let's say, a pair of particles, a two particle, okay, two particle, and their Hamiltonian is, the simplest Hamiltonian is S1 dot S2, dot product. Okay, so let me not do a this is just two, right? And this thing is called the exchange integral. It tells you how strongly they are interacting. Exchange interaction, let's call it integral. There is a reason to call it integral. I'll tell it later. Okay, so we want to ask. Notice that this is not the only way to write this. The point is how a Hamiltonian is a scalar. Theoretically, there are many other ways to construct scalar, and it turns out there are other ways, and there are different systems where you need to do it in different ways. But this is the simplest way, and there is also no reason to say that this will be two spin, right? It could be multi-spin, right? So those are all viable problems. They are more and more complicated, but this is the simplest one of all of them. Right? So now I want to write such a Hamiltonian. So what does this mean? So I expand it S1x plus S1y S2y plus S1z S2z. So this will act on this two particle state, okay? And this two particle state is plus minus plus minus. So then how do I write down? How do I write down this form? The way to write down this form properly will be J S1x direct product S2x plus S1y direct product S2y plus S1z direct product S2z. Okay? So there are two ways you can construct this. You can either construct it by the way we just learned, that I evaluate each of these terms. So what is S1x? S1 is sigma x with the h bar that I am not writing. S is basically h bar by 2 sigma, right? So I am not writing the h bar. So S1x is just this quantity. So we know how to evaluate this. So once I evaluate this will become, sorry, this is, yeah. So this is the x. So x is okay. Now I can evaluate it as a matrix form. So then it will become okay. I can similarly evaluate the second term. This would become the third term. And 0 everywhere else. Okay. So then I can combine all these three and write this whole thing, which will become, then the h is basically with some prefactor that I am not writing, that is coming from j and from the fact each of them has a h bar. So h bar squared by 4 times this full matrix, which I can get by adding these three, and that is okay. Yeah, what's the confusion? Okay, so this is what I'll get. Now, if you can immediately notice that this is a problem to do that, because that means if I give you, let's say, 10 spins, right? 10 spins means what will be the dimension? So for 2 spin, it is 2 square, 4, right? 4-dimensional Hilbert space, because each of them can take 2. For 3 spins, it is 8. Similarly, for n spins, it is 2 to the power n. So you can imagine, like if I have a 2 to the power n by 2 to the power n matrix, then already how complicated it is, how many operations you have to do to generate that. Right? Although in principle you can do that. So you need a smarter way to do that generally. So one thing to notice that so many zeros, right? So many zeros are here. Okay. So if you construct this 2 to the power n by 2 to the power n matrix, you know that there are going to be mostly zeros. So if you have a way to know a priori that, oh, there are so many zeros, I don't need to work that hard, right? So what can we do? We can look at simply observe the action of these operators. So let me tell you what is the operational strategy that we use when we want to describe such a system. That we do following. We evaluate each of these entries, okay? So we take this, we say, so first notice S1x is S plus the ladder operator plus minus IS minus, okay? Right? Where an SY, so let me remove the one for time. That is S plus minus. No, this is just S plus minus I. This is plus minus IS, right? So this is the form. So what is S plus? I think it is the other way. Yeah. So S plus is Sx plus minus Sy, right? What is the plus minus? ISY, okay. So this is a basis shift, okay? What I am going to do, the Pauli matrices forms a basis, right? The Pauli matrices form this basis, sigma naught is identity, sigma x, sigma y, sigma z, okay? Now we told earlier that the problem with x and y is that they are not diagonal. So I can construct a basis which rotates this Pauli basis in the xy plane. Okay? So it is like a 45-degree rotation if you picturize it, but in the plane of these matrices. So what do we have? Okay, this is the rotation. Now what does this job of sigma plus? Sigma plus acts on an up and sends it to minus. That's the only job. It flips the spin. So if I do that, so let me write everything in sigma basis. In sigma. So my S1x S1x plus S1y S2y will become S1 plus S2 minus what? Yeah. This should be sigma minus. No. Yeah. Sigma minus take it up to down, and sigma plus take it down to up. Right? So these is a ladder operator in the sigma space. That's what we learned last time. So yeah, S or sigma, whatever you can. Let me use sigma since I'm using sigma now. I can rewrite the x and y term in terms of this sigma plus and sigma minus. When I do, I get this. Actually, I get an additional factor of half. So now it's very easy to determine what happens to this because I want to calculate this plus plus. So then what will happen? These 2 minus will flip this second, right? So if I act this h on this, let's evaluate the first term. What will this do? This will flip this to minus. Plus means up, minus means down, and this will flip this to. This will leave it intact, right? No, this will give 0. So this will give you 0 anyways, right? Because up acting on up, plus will give you 0. So this will become 0, right? So similarly, this term will also make it 0. The only term that can do nothing is this, z. This is already a z eigenbasis. So sigma z, sigma 2z will be the only one which will give you something, some number. This will give you h bar by 2, this will give you h bar by 2, so h cut square by 4. This is what you will get. Okay? So this is the action of this. Now I can easily see that what will happen if h acts on, let's say plus minus, which is the second entry of this matrix. This entry. Okay? So if you can stare at it and immediately figure out that this is going to be 0. There is no term because the plus minus will make everything 0 anyway. Now even the z will make it 0, right? Even the z will contribute. So try to construct this matrix element by term, and then try to predict which one of them are going to be 0, a priori, okay, without any calculation. That you can do also. So this is the alternative way to generate this matrix, where I only generate the entries which I know to be non-zero. Right? Yes. Yes. Positive will give you 0, right? Because your sigma plus acting on up will give you 0, right? Because there are nowhere else to go. Yeah. So this part is actually the tricky. The only non-diagonal entry you will find here and here. Because why? Because they connect between plus minus and minus plus, right? So here the z term will contribute you to 0, but this will, so these are two terms which are connected by one flip. Right? So that's why only these two terms, only these two off-diagonal terms are going to be non-zero. Okay? So play with this thing a bit. It is like nobody can make you see this thing unless you do this calculation yourself. And once you do this yourself, you will start seeing pattern into that. And then you can do this calculation very easily. Like then you can generate this matrix. You can generate the elements on the fly instead of multiplying these big matrices. Okay? So this is a very interesting endeavor. So there is I have a collaborator right now. I'm working with them mainly. I'm collaborating with them because of his ability to do this for insanely big system. So he can do 50 spins, which is 2 to the power 50 by 2 to the power 50 matrices. This is the world record right now. Okay, and you can imagine they don't use any of these strategies. They have completely different strategies to do that. And what strategies they use is kind of not easy for me to tell or understand. And that's why they are in demand. Like you have to spend some time. I'll send you the paper. You can spend some time reading it and understanding it. That how do they break down this problem in a way such that they can go to this kind of sizes. Okay? And it's extremely important. It's a technical barrier, right? It's like why do you need to build LIC to study physics? Because you cannot go to see physics of that regime, that scale, unless you build such a you push some technical barriers, right? So this is a similar. So let's say you want to study a system, and you want to study system in thermodynamic limit, right? A thermodynamic limit means what? 10 to the 23 particles. So there is no way you are going to solve this problem, right? There is no way you are going to solve this problem. So what's the closest you can do? This is the closest you can do. And somehow from here you can infer what happens in this region. Okay? And it's very important to go to this barrier, to push this barrier as much as possible. And this thing is called the exponential barrier of quantum systems, right? So although you know the whole problem, that you can describe the problem, you can solve it. But to solve 50 particle, there is exponential cost. Right? Why? Because you are representing your. So let me spend another 2 minutes. That's where quantum computing comes in. So the idea of a classical computer is following, that you represent each state by a state of a classical device. Right? For example, if I think of a electronic computer, that state is basically a capacitor charged or discharged. Right? That is your 0 or 1. Right? So now if you want to represent this state of two particles, you need 4 classical states, right? 4 classical bits. Similarly, if you want to represent the states of n quantum particle, you need 2 to the power n classical bits, right? Because each bit contains one piece of information, right? Because they are classical, they are not superposed. So that means you need huge amount of cost. So if I think of this storage, so how much RAM I need? Imagine this is what it becomes costly RAM power, right? So 2 to the power n, like if you think of our standard computers, which has 8 GB RAM, there you can do probably 10 or 12 speed. Now we have a cluster that I got this cluster for this kind of work. I have 128 GB RAM or 192 GB maximum. There I can hardly do 20, 30, right? So now where quantum computing comes in? Now if your simulator itself is a quantum object, which means you are simulating one quantum object with another quantum object, not with another classical object. Right? So then you need n qubits to represent n quantum particles, right? Not 2 to the power n. You need n for n because they are also superposed. They are also superposed like that. So if you can run your simulation on this quantum simulator, or your computer itself is made of quantum particle in a controllable way, that means you can simulate n particle with n particle. So that's what that is one of the promise of quantum mechanics, quantum computing. It's the requirement of storage or requirement of complexity. Right? Also to manage 2 to the power n bits, you need much more complexity. Right? But to manage n bits, you need less complexity. But that doesn't solve all the problem. There are other problems also. What about the time it takes? How do I control that? Is there a universal simulator, right? For example, I am trying to calculate, let's say, motion of planets or motion of particles in a box, motion of particle in a glass of liquid, or motion of planets, right? They are two completely different kind of systems. Both of them follows Newton's law. Both you can simulate in the same computer, right? Now, that means what? There is a universal simulator. That universal simulator is the state of this capacitor. Right? So these capacitor states can simulate where you can encode both information about planets or glass of water or anything calculable classically, or is this quantum particles. So does this guarantee, is it possible to have a universal simulator? So this question was asked earlier. There is a paper by Seth Lloyd who showed that yes, there is a possible to have a universal simulator with few operations, right? So let's say when you have a quantum computer, so let's say I want to simulate a quantum dynamics, right? So that means I have a system in some high dimensional block sphere. It is located at one point, and the dynamics drives it to another point. Right? Now, can I have, and for any systems in the universe, can I have a simulator which does this job with another set of Hamiltonian? Because of course you don't have access to that Hamiltonian which you are trying to simulate. You don't have access to Jupiter's planetary motion in your computer, right? You have another set of operation which mimics that. That's the meaning of simulation. So then, is there another set of Hamiltonian which does the similar job? Right? That's the question of universal simulator. And what Seth Lloyd showed that with two quantum gates, with just two quantum gates, you can simulate any such local Hamiltonian. Local means things which interact with neighbors, not like far apart. And this idea is similar to saying that let's say I have a car that I want to park in this space. Now I don't have access to a motion that goes like this. If that would have been there, that would have been perfect, right? My car can move only forward, backward, and at 30-degree angle. It cannot move this way. So I need a bunch of operations which will do this, which will make this movement and fit it here, right? Depending on your skill, it will fit it here. Okay? So similarly, if I have a few set of operations using some laser pulse or something, some electrical something, can I simulate an arbitrary Hamiltonian? Okay? So it turns out you can if they are local Hamiltonian. And then there are various issues with that. That is what quantum computing people are trying to do. Okay, did you get the picture? Only set up few Hamiltonians, as few as possible. Yeah. Yeah. So the Seth Lloyd proved a theorem that such a thing will always exist. It's a mathematical proof, but then the question is how can we build that? So there are interesting projects that you can try here also. That how do I simulate this Hamiltonian? How do I write a program that will do this classically and then on a quantum device using this Qiskit and stuff? Okay, those are very interesting projects that you can take up. And one problem that I have been trying to do for a while is when they are not exactly local, which means multi-speed interaction model. So there is a model called JQ model, which has a deconfinement transition. You must have heard about confinement, deconfined transition in QCD, right? That quarks are confined and quarks are deconfined because they are like free when they are close to each other, but they attract each other when you try to separate them. So it turns out there are spin models where you can see similar deconfinement transition. Okay? So they are called JQ model, where you have this kind of J term and a term which is like singlet terms. So this Q term is effectively like 4-spin interaction term. Okay? And it's very tricky. They are not local. They are not like two. They are called 4 local. You can have K local terms like that. Okay? So how do you simulate that on a quantum computer? There are technical issues to do that. Okay? So you can try to think about that problem, but first try to do this on your hand, then on a computer, then try to think how to do it on a quantum computer and all that. This is a standard problem. You will find many people have done this already on quantum computer. But I think this is still an issue. Okay, questions? Okay, let's move on to the addition of angular momentum. And then we'll come back to density matrix and entanglement, because now we are really in a position to talk about how to describe. Now we are already talking about things that I have a two-spin system, right? Multi-spin systems and so on. So there, as I said, there are two issues. One issue is the space, that how much you need to, how many bits and complexity you need. Then another issue comes in time. Just because you solve the issue of complexity, that doesn't mean that if it happens that in quantum computer, to do the same job, there is nothing usually comes from for free, right? If you have saved somewhere else things have gotten bad. So you might ask that it turns out actually you need more number of operations to accomplish this job. So that means it takes more time. More operation means more time, right? So there are also ways, strategies to reduce that. Right? So when you try to go deeper into this problem, you will see all these things are will start factoring in. So Feynman was the person who popularized this idea, but before Feynman, this idea was there already, that it's possible to simulate a quantum system with another quantum system, and that will make you things much easier. Like for example, right now all these IBM machines, they have like 50 qubits, 100 qubits. But to do that means you can simulate a 50 size, 100 size system with that computer. But in order to do that in a classical computer, you need your 2 to the power 50, 2 to the power 100 classical bits. And but it's not so simple, because it's not easy to keep these things in a superposition state, right? How do you know that there will be some measurement or something is not disturbing it, or the system is losing its coherence? All those factors are very challenging issues. So it turns out there are noise in these computers, which means what happens that it tells you that if you do, let's say, 5 measurement out of 5, one will be error, one will be wrong. Wrong means one will be classical. Now then, if that is the state of your device, then how do you extract reliable information from that? Right? So that is a whole subject called error mitigation. How do you take a noisy result and extract meaningful result out of that? So all these things are issues with current state of quantum computer, which are called noisy intermediate scale quantum computer. And hopefully in future those noise part will reduce, and then you will get more reliable. But if you want to do any work with current computers, current existing computers, then you have to deal with that. Okay. Okay, there are some other things you can also do that, for example, in this exercise, just to gain confidence, that this plus plus, for example, how this plus plus looks like. Plus is 1 0, direct product 1 0, right? This is 1 0 0 0. Similarly, plus minus is 1 0 0 1. Right? So it is what? 1. This is 1 and this is 0. No, this is 0. 0, 0 1, 0 0. Right? Similarly, you can represent all the 4 states. So then you can check that will the sigma 1x, how will it act on this plus minus? You know this from here, that this sigma 1x will act on this plus, and flip it with the h bar by side. You know how a sigma 1x acts on a z eigenstate. But now how it acts on this joint eigenstate. So you have to construct this operator in this way. Right? You have to write the 4 by 4 form, act it on this plus minus in this 4 by 1, and you should get exactly what you expect from it. Right? So that will give you confidence that this machinery, how it works and all that. So do all this, play all those things, right? If you don't play with all these things in your own hand, you will never gain familiarity, and you won't be able to navigate in this kind of problems. It's just like learning a language. If you don't practice that language, you will never learn it. Okay? Okay, so now we will talk about another thing which we left out in the previous semester, on addition of angular momentum. So first I'll tell you how to construct this idea, and then eventually we'll learn that how to do it for any generic fields. Okay? So everything is clear so far, right? Do practice those things. Okay, I'm telling you again and again. Do practice means work out all these calculations by hand. Otherwise, your understanding will be superficial and you won't have any hands-on training. It will be like being in an operation theater as a doctor with only theoretical textbook knowledge of medicines. Okay, so it will be exactly equivalent to that if you don't do these calculations by hand. Okay, and you know how it is. If your doctor is like that, online educated. Okay, so let us say I have two particles now, okay, and I call the the operators for the first one as S1 and second one as S2, and each of them are separate, are two completely independent particles. Okay. Okay. One more point I thought I told you already, but I want to quickly mention as a side point that this idea is already you have used this two particle idea when you are describing a particle with multiple attributes and that they are not dependent on each other. For example, the position and x1, so x, y, z. So this is the position state, and this particle also has a speed. So you write it like this, and actually you write it like this. Right? This is the full description because the x coordinate and y coordinate and z coordinate are completely independent of each other. So and this way you can write it like that because they are all commuting. All of these are commuting, and spin is also commuting. Everything is independent, right? So that's why that idea you already used when you write it, this a full wave function that has position and spin. Now you won't be able to do that if it is. So for example, you will never be able to write xp x. Why? Because xpx are not like this. If you know x, you don't know the p. If you know the p, they are commuting observable. Okay? They are non-commuting observable. Right? So just to remember this idea, that you have already used that, extensively used that, but now we are formalizing. Okay, now I want to describe this two particle state. So let's say each of these particle, so that means I should be able to construct an operator, okay, this S1, which acts on this one state. So state of first one, and gives me h cut square S1 into S1 plus 1, S1. Similarly, S2 will, no, sorry, S1 square, and S2 square will give me and similarly S1Z. Okay, so this is two complete independent description which I can shorthand in this form. Generally, let's say if I have spin half, I write it as half half, half half, half, minus half, minus half, half, minus half, minus half. So I'm writing this in terms of this. Actually, sorry. I should not. I am not writing the joint eigenstate here. I'm just writing the SM form. So SM form there are only two possibilities. Half, because S is only half, right? It's not minus half. So half half or half minus half. So this I represent as plus and this I represent as minus, because this is the only difference. So if I want a joint eigenset, I can now construct it plus 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 minus minus plus minus minus. So now this plus plus means this is S. This is written in the form S1 M1 S2 M2. So that means it is half half direct product half half. So this is half half direct product half minus half. Right? This is the shorthand for this. Everybody got this, right? So now I want to describe this joint eigenbasis, which we have already done, and I want to write down the full form of that. Okay? So what should I do? So I can immediately see that if I just use these things, that I want this S1 square to act on this joint state. Okay. If it acts on this joint state, it should give me, let's say, plus minus. Okay. Because this is an eigenstate of this and this is this. Okay. So what do I expect to do this to do? This is square. Okay. What do I expect here? Sorry? Minus half. Why? No, this acting on this. This one I expect to be minus. Right? So I want to construct my operator in a way such that this is what I get. Okay? So now I also want this. So this is all the structure of these single particle operators. These are all single particle operators, right? So now I want to see the structure also for the joint particle operators, right? The combined operators. So there are two such quantities. Okay? There are two such quantities. One is S total. S total, which is S1 plus S2. So this S total will have its own algebra, like S1, Si and Sj. Si1, Sj1 has this operator, I, H bar, epsilon ijk, Sk1. So let me write it as A. So A is 1 or 2, which means each of these individual particle has its own algebra. Right? So I want this fat one, which is the sum of these two, also to have that, because then it's a joint eigenstate of the full object. I want this, okay, and I want to find the action of these operators. Okay. So what is this Sm? Sm is the joint eigenstate of these two particles. Okay. So we want to find the relation between. So basically, I want to ask that these eigenstates that we constructed, plus 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 minus minus plus minus minus, these eigenstates, are they also eigenstates of these operators? This is the question we want to ask. Okay. So let's check that. Let's check that if that is the case. Do you understand that what are we after? So we constructed the eigenstates of, we know the eigenstate of two individual states of S and S square. Okay. Then we constructed a joint set of states. Okay. And they are obviously, they will be eigenstates of this operator acting on this expanded basis. Now I want to think of an operator which is sum of these two operators. This is the problem of addition of angular momentum. I am adding this angular momentum. And I want to ask, what is the eigenstate of this operator? This will be also a four-dimensional Hilbert space, right? And this four-dimensional Hilbert space is already, we know that it is spanned by these eigenstates. They are the basis states of this four-dimensional Hilbert space. So then I want to ask, are they also, or if they are not, then what are the eigenstates of these two operators? So the problem of addition of angular momentum is basically the problem of finding the eigenbasis of these added angular momentum operators and finding their relation with these operators of individual eigengate operators. Right? Everybody got the problem that what are we after? Online audience, are you completely clear about the problem? Yeah. So let me write it down here more clearly. So the problem of addition of angular momentum basically find the relation between the eigenbasis of total angular momentum operator and the eigenbasis of direct product of individual angular momentum operators. Yeah. Did you get the statement of the problem? If you have got the statement, the problem is half done because the rest is very easy. Okay. So let's find these joint eigenbases and find its relation with these eigenbases, the total operator. It's a very simple linear algebra exercise. So let's start by saying, let's start by finding the action of this total operator on each of these states. Right? So what is this? Sz1 plus Sz2. What will it give me? Yeah. So it will give me h bar plus, right? So this is an eigenstate. But do you know how you should do it actually? This one you know, right? Right? So this will give you h bar by 2, this will give you h bar by 2. But if you want to write a matrix form, it should be written like this. Because this has to be 4 by 4, right? Then it can act on this class. This is the actual form and this is the shorthand. Okay? You should always keep it at the back of your head. Okay, what should this do? This is the fat SZ. What should this give? Yeah, this will give you 0. So this is 0. Yeah. Similarly, SZ minus plus will give you 0. SZ minus minus will give you minus h by 2. Right? So that means this basis. Yeah, what? Yeah, minus h by 2. So that means this basis is also an eigenbasis of the SZ operator. Right? So this much we got. Now what about the square operator? Everybody got this, right? You should be able to do these calculations eventually in your head. That's the goal. And for that you have to practice. And I find it very weird to write this down because I usually do this in my head. And then writing it down again, it feels like that, weird. It is like when you start to read, you read each letter, right? You say some spelling, apple, A, P, P, L, E, right? And then when you grow up, if you read it as a word, then you grow up a more, you can read a whole sentence just like that without individual word. And there are stories of Swami Vivekananda that who could read a whole page like that. And then he could read a whole book in a very short time and also memorize it. So your goal is to reach as close as possible in this front, as close as possible to that. And that happens through practice. Okay? I think now I can read maximum a paragraph like that. But of course, somebody who have trained their mind to do non-trivial things, they might be able to read a whole page or something. Okay, so now I want to know what about. Now notice that there will be, we know that what are we going to get, because when you are adding these two angular momentum, two spin half, there are two possibilities, S1 and S0, that we know already, right? So the total S is either 1 or 0 plus when you add two half or when you subtract two halves. And the M corresponding to this, we know that, and this is 0. So this is what we are getting, the same thing by this algebra. Okay, now this S square. How do you determine the action of this? What will be the steps? Sorry? What? How do you calculate the action of S square on this? No, that's where probably you are not thinking. Online audience, how do you do that? What is S square? It's not S1 square and S2 square, right? S2 square. That's where you get this S1 dot S2 now, right? We already learned how to handle S1 dot S2. So this is S1 square plus S2 square plus S1 dot S2. Okay? S1 dot S2, 2. Okay? So now I can determine the action. Now this is tricky. S1 square is simple. S1 square will give you, these two will simple. These two will give you 3/4 h cut square plus 3/4 h cut square. Right? These first two. Right? What about the second one? The second one, you can write S1, S2 minus. Sorry, plus. Yeah. Okay. So now what about the second one? Even if I had plus minus, this wouldn't have changed because A square is A square. Okay. How does this act? So S1 plus acting on plus will give you 0. Right? So that will happen also for the other two. So you will basically get similarly you will get S square. So far so good, but you will find A square plus minus will not take you to anything that is plus minus. Can you see that? You cannot see that now, but if you do those S1 dot S2 exercise I told you earlier, then you can see that. Okay, so try to show that. So I leave it as exercise. S square acting on plus minus or minus plus will not give you anything proportional to plus minus or minus plus. What does this mean? This means this plus minus and minus plus states are not eigenstates of this operator. So that means I have to just rotate that to find the eigenstate. And that's where some non-trivial relation will pop up. Okay? So the conclusion is following. This plus minus plus minus, they are not joint eigenstates of S square and Sz. The fat S square and fat Sz. So we have to have a relation between them. So the adjoint eigenstate of these two is Sn. So they must be, now this one forms a complete set of states that we know. Right? This set of state is S1 M1 If I sum over this whole space, this is identity because they are eigenstates of this joint operator, so they must form. They are basically 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So they are eigenbasis of this four-dimensional space. So there must be a relation between these two. So I'm writing it as M1, M2 because this plus minus is just M1, M2. I don't need to write the S. They are half always. Okay? So these coefficients, they have a name. I always pull up this way. Klebsch-Gordon coefficient. And we'll see how to find that. We'll see how to find it for half. And there is a nice table which tells you how to find it for everything else. Okay, so you have to learn how to read this table. People painstakingly found this. Okay, worked it out. Somebody worked hard for this table. Okay, so let's see how to find this for one case, and then I will tell you how you try it for some other case. Then you know how these tables are made, and they are very useful tables because you are always dealing with this kind of problem in physics and chemistry everywhere. They are always multi-electron orbitals, right? Multi-electron atom. What is the total angular momentum? You will that multi-electron atom will give you in experiments. Very important problem. Nuclear physics, chemistry, everywhere. Okay. Okay. So let's see. This is we already actually almost solved the problem. We just have to write it down in a nice way. Don't get intimidated by it. It's very simple. Yeah. Huh? Yeah. It's a square is basically identity. 3/4 3 by 2 a square is basically acting on any state gives you what 3 by 2 is by square 3 by 4 of that state. A square commutes with all the operators in that spaces, right? In that space. So this is equivalent to an identity operator. That's what we learned in the previous semester. And you can also show it. A square is what? Sx plus sx square plus sy square plus sz square. And if you put them, a square of any Pauli matrix is basically identity. Yeah. No, this joint one, this joint identity, it is not. Yeah, joint one is not diagonal in this basis. Not in this basis. It is for individual basis it is, but in this joint basis it is not diagonal. Okay. So there are actually various other interesting way to think about this product of matrices, which I can tell you sometimes later. First you practice this, get it in your head, then you will see that there are various other way to do these calculations. Okay. So now I want to find this. So the simple way to what is this? This is basically the matrix element between two defined M1 M2 because I can write it as M1 prime into prime Sm. And this is nothing but, so this is M1 and M2. Okay. And this we know, this thing is delta M1 prime, delta M2 M2 prime, because this is orthonormal. If this half minus half sets, these sets are orthonormal, so this must be true. So what is this A same M1 and M2? It is basically this matrix elements. Okay. So let's calculate some of them. Some of them are trivial, some of them are little work. So now notice what are we after? We are after these Sm states. So we are after we told earlier the problem of angular momentum addition is finding the relation between eigenbasis of this joint operator and this the operator finding the relation between the eigenbasis of this joint operator and the direct product space of the individual operators, eigenbasis of the individual operator. Right? So this joint operator Sm, their angular momentum states are 1, 1, 1, 0, 1, minus 1, and 0, 0. So this is this set. This is what I call Sm, and this is my M1, M2, which is basically plus, 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 minus, minus, plus, minus, minus. So I want to find this relation. Okay. Now so let me write it in proper form, bracket form. Okay. Now some of them we already found because we saw that this plus plus is same as 1 1, and minus minus, no, not minus minus, which two are same? Yeah, minus minus is same as 1 minus 1, right? Because these two cases we found that S square and Sz, they have exactly the same eigenstates as they have exactly the same eigenstate as this plus plus and minus minus. Right? Everybody got this point? We found that all these fours are eigenstates of Sz, the joint Sz, the summed Sz. But only these two are eigenstates of this summed S square. Right? So that means these two must be equal. Everybody got not so appreciative phrases. Online audience, did you get this point? So the only two things we have to find is these two. The relation between 1, 0 and 0, 0. And these other states, plus, minus, minus, plus. Only these two things we have to find. Because we have already shown that Sz, all these things are eigenstates of Sz, joint Sz. And we have already shown that this plus plus and minus minus are eigenstates of this. And this plus plus is basically 1, 1. And minus 1 is basically 1 minus. Okay? No, it's just because I've written it like that, that doesn't mean they are this. Okay? 1 minus 1 is this. If you want like that. Okay? Because they are adding, you are adding two minuses, right? So it has to be the minus 1. And that we have already seen also. Okay, so how do I find that? So notice that S plus acting on 1, 1 gives you 0, and so does S minus acting on 1 minus 1, right? Because this is the bottom rung and top rung. So now we find the action of S minus on 1, 1. Okay, what it will be? Remember the formula. Remember this formula. S plus minus acting on Sm gives you H bar. Do you have class after this? Okay, let me complete the spin half only. Just it will take another few minutes, 5 minutes max. Remember this formula we worked out in the previous semester, that if I have to go from Sm to 1 Sm plus or minus 1 up or down, this will be the p-factor. So I use this here. Okay. So if I use this here, what I'll get? I'll get H bar root over 1, 1. So 1 into 1 plus 1 minus 1 minus 1, 1, 0. So this is H root 2, 0. Okay. Now I add this on the other side. What will be on the other side? Other side will be S1 minus plus S2 minus acting on this plus. 1, 1 is plus plus, right? 1, 1 is plus plus. So now what it should give me? it should give me S1 minus acting on plus 1 direct product I2 acting on plus 2. This will be the first term, right? The second term is I1 acting on plus direct product S2 minus acting on plus, right? Everybody got this? Make sure you understand everything I'm doing right now real time. You won't find a simpler example anywhere. Okay? If you are stuck here, you have no hope of going through this chapter. So ask me as many times as possible. And make sure you get every single step of the algebra. Clear? Online audience? Okay. And all these steps will be jumped in the textbook. That I can also assure. Okay. Now, how do I find this? I have to again use this formula, right? This plus means now half, right? So I have to add this formula on half, right? So what will I get? I get h bar half into half plus 1 minus, I wrote this note in a type form, but there are errors here, so that's why I'm not sure about this in some steps. Minus 1 plus, right? This plus will go to minus because it's a down operator, and the plus will remain plus because of identity, right? Similarly, there will be a similar step here, which I'm not writing down because it's wrongly written in minus. So what will happen? It will go to a plus. It will go to a some plus, something times plus times minus, because the S2 will take the second part to one step down, right? So let me write the final form. The final form will be this. And the final form will be h bar minus plus h bar plus minus. Very simple. Final form will be h bar plus minus h bar minus plus, this is minus plus, and h bar plus minus. This factor is h bar. Okay. So now that means what? So that means,
Sir,
yes.
students for next class have come.
Sorry?
Students for next class have come here.
Okay, so yeah, so then you can close it there. Yeah.
Okay.
I will just write down the last few steps, then you can take it up on the recorded version. So what did you get? You started with this h bar root 2, and this side you got h bar plus h bar minus plus. So that means 1 0 is 1 by root 2 plus 1 by root 2 minus plus. So I found the relation between 1 0 and plus minus and minus plus. Okay. Now I can play the same game and figure out the 0 0. It will become this is your singlet. Okay. Up down minus down up. Okay. Now let me just write down everything in a familiar form. So one more step I want you to notice, that in this relation, our original agenda was to find SM related to A, SM, M1, M2, M1, M2. This was our original agenda. Now notice that this M will always be a sum of this M1 and M2, which we know already intuitively because this angular momentum has to be conserved, but you can also show it. You can show it by writing Sz acting on Sm will give you H bar. S1z and S2z will act on this, will give you H bar A Sm M1 M2 M1 plus M2. So it will always get this thing. This is this MSM. It will be equal to this. Okay. So now I can write this one step simpler. I can just write this as, since I know that M1 and M2 must sum to M, I can write this as Sm A Sm M1 M2 must be M minus M. So that's it. M1 and M minus M. Instead of writing M1 and M2, I just write this. And then I just sum over M. And that's what I have found here. So what did I find? One is plus plus. That we already found. That means A Sm is 1 and M1 and M2 is half. This is 1. First Krebs-Gordon coefficient, we found this to be 1. So 1 0 is 1 by root 2 plus minus plus 1 by root 2 minus plus. Okay. So what does that mean? That means A11, this is 1.5. So that means this minus half is equal to 1 by root 2, and A11 half minus half is also 1 by root 2. Right? Sorry? Is 1 0, right? That's what we found. That relation. This is this relation. This relation. I'm just writing this. What is the problem? I didn't get it. Oh, okay. Yeah, you're correct. So this would be 1 0. And these two must add to 0. So 1 minus 1 similarly is minus minus. So that means A 1 minus 1 minus half is 1. I can find the 0 0 also without any work, but I will not show this, that will take time. So 0 0 is just 1 by root 2 plus minus 1 by root 2 minus. And that also is some F coefficient of that. So there is a way to find the 0 0 without doing much calculation, because you know it is 0. So this has to be a sum of plus minus and minus plus. And you also know their sum of square must be equal to 1. And you can also show that just by acting this this state, that 1 0 with 0 0, we know that this is 0. So you can take these products, you know they has to be equal and opposite. Yeah, minus plus. Okay. You can use this to find it from this, just like your second assignment of quantum mechanics 1, like this thin 1 assignment. Okay. So this is this Krebs-Gordon coefficient. Right? We learned how to find it. Okay, now your exercise is do it for 3 by 2 and 5 by 2. Okay. Even the half is not worked out anywhere. Okay, I will stop it here. Next day I will talk a little bit how to write it down for general J and tell you how to read this table. Okay, you can Google it, it's in Wikipedia or any book appendix it is given. Okay. To find this relation between an arbitrary pair of, how to do this basically. I have a J1 M1, J2 M2, not half. How to go for this JM? How to go from here to JM? And then the question is how to do it for 3 spin, 4 spin. So there are interesting group theory underpinning of this exercise. There is something called Young tableau. If some of you are interested, you can read this. People look at these higher order particle multiplets In particle physics, they are extensively used. They are a very nice way to construct things. There are geometric patterns into it, but we won't have time to go into all that. Okay. I will next class. I will just tell you how to do it for general J and M, and show some example, and that's where we'll stop. That's all. Yeah. Why did you go by a news article? Why not something concrete? Harness time reversal to measure vibrating. Yeah, sure. Sounds interesting. What is the paper? Show me the paper. You don't show the news article. Yeah, so send me that in Piazza. I'll see that. Okay. These news articles, especially the one which is written in US, they are always blown up, and it almost always confusing. You go to the paper. Yes.
How would you actually operate this method? Like, so we basically write it as cross one, uh, uh,
This operator, right? Sigma 1,
sigma one plus.
sigma 2 minus. How do I act it on this?
Yeah.
On a plus plus.
Yeah.
So this is just this. Right? See that. Yeah. Yeah. No, up will give you 0. It's wrong. Wrong. Maybe I've written it wrong. Right? Yeah. So sigma plus on up will give you 0. Right? Sigma plus on down will give you up. This is just a 2 level, right? The plus will bring you down. Sorry, minus will take you down, and plus will take you up. But if you act plus again, you will go nowhere. If you act minus again, you will go nowhere. Right? That's why they should be. Yeah, just like ladder operator.
For the term paper, actually got this review article.
Pauli exclusion principle and the problem of its experimental. Okay, I have no idea about this article. You can send me that. Yeah, what is the problem with it? There are so many proof. The whole chemistry is proof of Pauli exclusion,
Yes. So they're
right?
using group.
Chemistry exists, we exist. So that's proof. Okay. What?
That's why actually the particle physics.
Huh.
So basically they prove that body is excluding violated and manipulated.
Okay.
So they're actually using
For fermions.
performance.
Okay. How did they then sound species? Okay. Tell me.
Okay. So,
This journal is also not a very good journal. Okay. Okay,
in
fine.
the symmetric group, right?
Yes.
Permutation is a subgroup of that. So using that, they're telling that either a wave function can be symmetric or anti-symmetric.
That's what I will discuss next.
Yeah.
It is only true in 3D. In 2D, there are more possibilities.
So they're telling that so if it is symmetric and anti-symmetric, they can get a permutation group, a group out of this group. But for a non-poly electron,
Yeah, there is parastatistics, right? That's what we'll talk in next 2 classes. Parastatistics and all that.
so in
Yeah.
that concept, we found that like for, it can be expressed in multi-dimensional.
Yeah. So the point is parastatistics exist in theory, but it doesn't exist in nature, in 3D. So that's why this is called the symmetry principle. That tells you all particles are either boson or fermion. Although theoretically there are more possibilities, but that doesn't exist. So this is a postulate, not a proof.
How about going
I have no idea. I have to look at this paper. Send me that in Piazza. Yeah.
to one more?
But there is another interesting thing. If you want interest in statistics, you can look at that. So so there are 2 ways to think about statistics. One way is to think how you exchange 2 particles. If I have 2 particles, how do I exchange them? Right? If I exchange them, it pick up a phase. Right? That phase tells you if function is symmetric or antisymmetric. That's what we will learn in next few classes. Okay? Now there are another way is this Pauli exclusion, which tells you more than 2 particles can fit on one place or not. In 2D, actually, there are many more possibilities in this. You can do You can pick up an arbitrary phase. They are called anions because it's any phase to any one. So in fact, it is interesting. Let's say you take a pair of particle and you try to exchange them, and you reach here. So this is time axis. Okay, you reach here, and then you exchange them again, and you come back. It's basically a double exchange. So you can show if in this case these lines can form a knot that cannot be untangled. Okay? This has so history of exchange is irreversible.
So it cannot go to symmetric.
No, you can. So exchanging this is this and this, right? After extending, if you do the exercise, then if you do it using a thread, these threads will become tangled. And you can, if you can untangle that thread, then they are different from the cases where these threads are tangled. They are called two different topological classes. So you can study one thing that how this kind of exchange is related to Pauli exclusion principle. How it yes, and there are general version of Pauli exclusion principle. Let's say K exclusion, which means not two but K particles you can put. After that you cannot put. So more general version of Pauli exclusion and this wave function exchange. So I'll send you some paper. Frank Wilczek worked on that. So this is an interesting point of view to think of. Now notice this only happens in 2D. In 3D, I will explain all this in class. In 3D, if you exchange two particles, so for example, let me tell you the issue with 2D. So if I exchange two particles, I exchange them, and then I exchange it again, right? You can view it like as if one particle is taken around the other particle. So from this particle point of view, it's like taken around. Now this loop, now if it is a 2D system, then from this particle's point of view, the other particle perform this. Now if you shrink this loop, you have to always cross this particle. But in 3D, you can shrink this loop without crossing that particle ever, because you have an extra plane. So that's why in 3D they are very trivial. In 2D, this history is non-trivial. There's another way of seeing this. Okay, so this gives rise to a new kind of wave particles called anions. So there are and there is no 3D in nature, right? There is no 2D in nature actually, but you can in condensed matter you can create 2D systems by these heterostructures, which is basically an interface of two materials. Okay, you can show that there are systems where all the particles can only move here, but they forbidden means there are some energy cost and or there are some reason that they cannot be mobile as they enter the material, only at the surface. Right? So they are actual 2D systems. So there you can in principle create such kind of systems. Okay? That's why the symmetrization postulate doesn't work here. There are more possibilities here, parastatistics and all those. So those are very interesting direction to think in terms of statistics and all that. And there are experiments people try to do. What will be the signature of this thing in a current voltage measurement? So there are various controversy related to that. And people try to construct experiments, and somebody else says, no, this what you are seeing is not because of these or because of something else. It's a very ongoing and hot field. But it turns out these things have something called topological protection, which means that these properties, they are, whatever happens in between, they are divided into two classes. Either you can cross it or you cannot, right? And they have some connection to quantum computing and all this. So those are very interesting.